and start recording the office hours. Yeah, so what questions did you have for me?
So I wasn't really sure how to do like the stuff on the homework. Like I wasn't even sure if the that I did for part six was even the correct answer with the max operand time frequency. So I'm not really sure how to do the rest.
And that was for homework 6, right?
Yeah. For the exercise 3.33 or
Okay,
number one.
let me go ahead and pull that one up. Okay, 3.33, that first one?
Yeah.
Okay, let me just make sure that I have, and part A specifically?
Well, I also B through C B through D as well.
Yeah, because I believe that's for homework 7, right?
Yeah.
Okay, yeah,
Yeah.
we
So
can talk
I'm
about those.
I'm assuming B through D won't be correct if I don't have A correct either.
For the most part, yes. Yeah. Um, Let me go ahead and. There we go. Do you have a copy of that problem in front of you? Because if not, I'm
Yes,
not
I do.
gonna. Okay, cool. So I have my own over here. I'll be looking at. So this one is the one with the chained XOR gates that are fed from 4 input registers and then lead to 1 output register. And for part A, you're asked to find the maximum operating frequency of the circuit. So what I'll do here is I'll pull up a pad. There we go. Okay. All right. Well, I think what I'll do, for some reason, my software doesn't want to capture that screen, so I'll do it over here instead. This is some leftover stuff. Okay, cool. So what I'll start with is drawing out the diagram really quickly. So there are that's strange. That'll do. Okay. So like I mentioned before, there are going to be 4 registers that are inputting to a bunch of XOR gates. And each of these XOR gates are chained one after another. And while I'm drawing this out, could you tell me what it's asking you to find?
For A, it's trying to find the operating sequence or frequency, which is TC, I believe.
That's exactly right, yeah. So, in order to find TC, what's the equation that we have?
It's TC is greater than um T clock to Q. No, contamination. Yeah, contamination clock to Q.
It'd be propagation clock to Coop, yes.
Oh. And then plus the propagation delay,
Right.
um, plus the hold.
Not quite the whole time, but the setup time.
Oh, okay.
Yes, let's talk about each of these components really quickly. So, TPCQ, that's the longest time it can take to be read out for a signal to go from the clock to being read out of a register. Because what happens is each of these registers receives a clock edge, and at that positive edge of the clock, it's now the job of the register to read out the next value to this wire here. And so, because of that, there's a small delay associated with the time it takes to go from saying, oh, the clock just struck, to, oh, now output my value that's inside. So that's what this TPCQ is. And the P just means it's the propagation time, and the propagation time is just the longest time associated with that. So for the delay, there's also contamination. There's also a contamination clock to Q, and that's the shortest amount of time we can go from the clock being read in to outputting the value of the register. Okay, so that TPD consists of all these guys, or TPCQ, pardon, and then TPD, that's going to be the longest path through my combinational logic between registers. So if you had to guess, what looks like the longest path here?
The first from the first register.
Yeah, from the first register, or even the second one, actually. They'd both be the same. But from the first register through one XOR gate, through the second XOR gate, and then through the third. And how much delay is that?
That is the total propagation time for each clock added together.
Yeah.
Or not clock, from each gate added together.
Exactly. And what's the propagation delay for one XOR gate, according to the problem description?
It's 100 picoseconds.
All right. So since there are 3 gates chained up together, that's 3 gate delays of 100 picoseconds. Sounds good?
Mm-hmm.
Okay. And just so that I can write it in, the propagation clock to Q time is, I believe, 70 picoseconds. Do you see that same value on your problem?
Yes, 70 picoseconds. Yeah.
Okay. And then what's our setup time?
Is that the time it takes for the the last gate to get the next value? Or
Not
the last gate to get,
quite. That's very close,
or, not,
though.
or the last register to get to receive the combinational logic
Yeah, that's pretty
signal?
much spot on. So TPCQ represents the first kind of reading out of a register. TPD represents the delay through each of our combinational gates. And then T setup, I'm going to word it a little differently than what you did to be very exact. But whenever you have a clock edge on a register, well, a few things happen. Firstly, clock edges aren't perfectly, they don't rise at a perfect 90-degree angle. There's always some rise time associated with them. And also, registers can have like a little window around that rise time where they could read in the value at any time in that interval. And that interval is called the aperture time. Aperture in the same sense that you'd think of when you're talking about like a camera. So this is the aperture time. The time before, so the earliest time up to when the actual clock edge hits, that's called the setup time. Whereas the time from the clock edge hitting after is called the hold time. So the setup time is the time before the clock edge hits that your signal needs to be there and stable in order to be read in. If your signal that's being read in is unstable during this interval, the register could read in an incorrect value. So that's what the setup time is.
Okay.
And in this case, what are we told the setup time is?
It's it is 60 picoseconds.
It is, and I believe I agree with you, it says the setup time is 60 picoseconds. So I'll write that in here.
So is the whole time? Oh wait, okay. I see.
Yeah, so the setup time is the time before that you have to be steady, before the clock edge, and the whole time is the time after the clock edge that you have to remain steady. So during that entire interval, your signal that you're inputting, whatever's on this wire here leading into the register, has to be a stable signal.
Does the setup time ever like vary, or is it just the max time? Like
I believe this is just the maximum time.
Okay.
There is some variance. It could basically maybe sometimes for your register you'd be fine getting away with only having it steady here, for example. But in the worst possible case, you definitely need it as far as this time. And so that's what they typically put on data sheets, the worst possible case.
Okay.
Cool. Yeah. Any other questions?
No, that makes sense.
All right. So now all we need to do is say, well, if we're going to have a clock time for this entire circuit, well, the period of our clock needs to be at least the same as or greater than all of these delays. If it's shorter, then the signal's not going to have enough time to propagate through the longest path and actually get read into the register at the end. So we need to make our actual full cycle time longer or equal to that. And so that's why this equation is the way it is. Okay. So now I can add these up, and I'm going to get TC greater than or equal to, I have 300 picoseconds, and then 70 and 60 make 130. So in total, that's going to be 430 picoseconds. And this is the minimum period. So that's the shortest period we can go. Now, how do we find the maximum the maximum frequency?
Is it 1 over TC?
Exactly. So the max frequency is going to be 1 over TC, which is FC, and I'm going to just call it the maximum. So the maximum is going to be 1 over 430 picoseconds. And then at this point, you would, plug in that value into a calculator, and you should get something around 2.2 gigahertz. That'd be 2.2 billion-ish. So I'll go ahead and actually plug that in myself real quick, just to verify.
So how would you type that into a calculator? You just put in 1 over 430?
There's a few different ways to do it. So the way I would do it is 1 over 430 picoseconds. The picoseconds, that unit, stands for 10 to the minus 12. So this is really saying 430 times 10 to the minus 12 seconds. Just as a reminder, the milliseconds, milli means 10 to the minus 3. And then you have microseconds, which is the little fancy U symbol. And then nanoseconds and picoseconds. These always go in increments of 3. That's typically the standard for engineering units. So that's 10 to the minus 9, 10 to the minus 12. And you can go lower than that. I believe the next one down is femto, but you won't really deal with femto units with seconds. It's just a very short time period. Anyways, so in my head, I would say, well, when you're dividing by 10 to the minus 12, you can flip that up to the top and make its exponent positive, because a negative exponent means you just take the reciprocal of that number. So on your calculator, you can plug in this, and you'll get the exact number in hertz. And then if you want to express it in gigahertz, you can divide it by 10 to the 9. So if you wanted this number in gigahertz, and you divide it by 10 to the 9, it'd be the same as doing 10 to the third over 430. That's how many gigahertz it would be.
Oh, okay.
And so it's 1,000 divided by 430, and that's how you get about 2.2. It's, when I calculate it, though, I got 2.32 gigahertz.
Okay, that makes sense. I was having trouble getting to the gigahertz.
Yeah. I mean, you could plug it in your calculator like this if you wanted to. It would just be a really, really tiny number, and it'd be kind of hard to deal with. So there's multiple ways of going about it, but this way typically is not too bad. And then you can figure out how many 10 to the thirds go into it and just go up that many. If we went one stage further, that'd be a bit too much, because then you'd be 1 over 430 terahertz. That's the next step up. But that's going to be a kind of a small number, which is why I stuck with gigahertz, where this is going to be 2-ish. Let's see. Yeah, that's about it for this calculation for the first part of the problem. And let me erase everything. Okay, well, while I'm here, what's the next step I want you to do for part B?
Uh, it wants us to find out how much clock skew can the circuit tolerate if it operates at 2 gigahertz.
If it operates at how much?
2 gigahertz.
Okay, cool.
So is it TC minus clock skew?
Not quite. Well, we have to consider the orientation of this queue. So actually, what I'm going to do is I'm going to go back to this one. You'll notice that I actually left out one step. And the reason why I left out that step is because I knew that it already would work, but you guys won't know that on your test. So I'm going to talk about it real quick. You'll notice I just did the calculation for the clock time. But you guys have another timing equation. Do you remember what that one's used for?
Its T hold is less than contamination clock to Q plus the TCD.
That's right. Now, just as a quick recap, this equation down here is meant to figure out the longest time that it takes you to go through your circuit. This is like the worst case scenario in terms of timing. This is the longest it could possibly take you to get through your circuit. And we base our clock time around that. This is the quickest path through your circuit. So that's what the C's stand for. Contamination delay stands for the fastest path. So actually, what is the fastest path through this combinational logic?
The last register.
Yeah, this guy, because you only go through one register, right? So this here, this CCQ and this TCD are replaced with different values. TCCQ, that's just given to you like in a data sheet or in this example in the prompt. The contamination clock to Q value is, I believe, 50 picoseconds in the problem.
Yeah.
And TCD, we just said, is one gate delay. And so one gate delay, for the minimum possible gate delay, it's not 100 picoseconds, but the contamination delay of a gate is how much in this problem?
It's 50.
I think it's 55. Let me check again.
Oh wait, you're right, it's 55.
Yeah. So that means our T hold needs to be less than or equal to 105 picoseconds. Does that sound all right with you? So with that in mind, what is our actual T hold value? What does it tell us it is?
It's 20.
Yeah, the problem says it's 20 picoseconds. So as a question to you, is this hold time constraint met?
Yeah.
Yeah, 20 is less than 105, so we're good. If this failed, all that means is that our entire circuit would not work at any frequency. So it wouldn't work. And so typically when you're doing your problems, you want to do this calculation first, because if you do this one first, then you might not even have to do the clock time at all. Because if this one fails, you don't need to then do the clock time.
So if the constraint wasn't met, does that mean that the it's trying to sample the clock before
Ooh,
setup time
yeah,
is
good
done?
question. So here's what's happening if your hold time constraint's not met. So remember that the hold time literally meant, here's my clock edge, and I need to remain steady after the clock edge hits. So we're looking at it from the perspective of this register here. So on this wire is the value that I'm trying to read in, and my clock edge just hit, so I'm trying to read in the value into the register. And I need a delay of a hold time amount before I can guarantee that I've fully read it in and nothing bad's going to happen. So that's what that means. Now, let's think about what happens if we have a signal coming from this register, register 4, and it's propagating really quickly through the logic. So it goes through this clock right here, and let's say that the contamination clock to Q was actually 10 picoseconds. Let's do 5 picoseconds. So it takes 5 picoseconds to get read out of the register. Okay. And then it goes through this XOR gate. And let's say it takes 10 picoseconds to go through that XOR gate. Now, after 5 plus 10, that would be 15 picoseconds. This wire and the value on this wire has now changed, right?
Mm-hmm.
But what we just said is that our hold time is supposed to be 20 picoseconds, but we just changed it in the middle of that hold time. And so now the register value that gets read in might be wrong because we changed the value on this wire that it was reading from during that hold interval. And
Got
so
it.
that's why the hold time needs to be shorter than the smallest delay. Because if the hold time is shorter, say the fastest path through it was over here, well, that's fine because my hold time is still less than that, and we're not interrupting the hold time. That's what it means physically in the circuit.
Okay.
So very good question. But that's kind of the purpose of these two equations. This is just to check if anything's going to work at all, because if you have it so that your fastest possible path violates the hold time constraint, it doesn't matter what clock cycle you choose, the hold time constraint is going to be violated all the time. There's always a chance that your signal propagates through in the fastest possible mode and your circuit just doesn't work. And so if this is not met, then our answer to the question would be no frequency, or no frequency is viable. Because it doesn't matter what clock cycle I choose, I'm always going to have a chance of having my circuit not work. And therefore your circuit doesn't work. Let's see. So yeah, that's if the hold time constraint's not met. And so what we're asked right now is okay, we're adding skew to the circuit. So do you know what clock skew is?
It's there's like a delay between like separate clocks, or like if there's like multiple clocks, there's a difference in the time it's sampled or something.
Those are pretty
It
close.
hits.
So typically, if you have multiple clocks, that's a different problem. If you have many different clocks, that's clock domain crossing, but we're not getting into that right now. There's just one clock. However, the clock being sent to this signal, and this signal, and this signal, and this signal, and this one over here, to all these registers, it's the same clock. However, due to delays in traveling through wires and maybe positions on a circuit board, the signal might arrive sooner to some registers than they would to others. That is clock skew.
Okay.
So what we're asked is, what's the worst possible clock skew that we can handle and still run at 2 gigahertz? So now I have a question for you. We've been adding a bunch of the terms to the right-hand side of this equation, but we could also add terms to the left-hand side. What would be worse for the clock time if we added extra values on the right-hand side, or if we added extra values for the to the left-hand side? What would be worse?
If there was skew, it would be on the left side.
So let's analyze it, yeah. So if there was skew over here, before we said 430 picoseconds, right?
Mm-hmm.
Let's say there were 10 picoseconds of skew. And let's solve for TC again. Well, this value is still going to be 430, right?
Mm-hmm.
Then we're going
And
to...
then you have to subtract 10.
Yeah, so now the new value is going to be 420, right?
Yes.
This is actually better. And it doesn't seem like it immediately, but this is the period. That's the length of your clock cycle. So if it's 420 picoseconds, I'm going to exaggerate it a little bit, the clock cycle has now become shorter. So it can do more operations per unit time. Or in other words, if we do 1 over 420 picoseconds, we're going to get, instead of 2.32 gigahertz, 2.32 billion operations per second, we're going to get something like 2.5 gigahertz, which is 2.5 billion operations per second. And that's faster, right?
So shorter clock time means faster.
Faster frequency. Yep. They're always
Okay.
inversely related because literally frequency is equal to 1 over t. So if the period decreases, the frequency increases and vice versa. So this is actually the best case skew for the clock time. That's what we'd like to happen. theoretically. Because if this happens, then that means that our period can be shorter, and so we can do more operations per second. Sound good?
Yes.
Okay, so our skew for the worst case scenario would actually be adding over here. And we can see that again by saying, well, if it was 10, we'd be adding 10 to the 430, so we'd have 440. And so it'd be 1 over 440 picoseconds, which would then be like something like 2.1 gigahertz, as an example. And that runs slower, 200 million operations less per second, because it's only running 2.1 billion. So this is the worst possible skew. And that's what the analysis is trying to indicate. We're asked if what's the most skew we can tolerate and still run at 2 gigahertz. If you put the skew on this side, you can skew it up as much as you want and it won't matter. But on this side, there's a limiting factor. You can only go so high before you're not at 2 gigahertz anymore, right?
Mm-hmm.
So let's figure out how much 2 gigahertz is in period. So 2 gigahertz, 1 divided by that, that's going to give us our TC, the maximum TC that we can go. And you can plug it into your calculator, but I believe you should get 500 picoseconds if you try it. Okay, were you able to get the 500, by the way?
I do not have a calculator on me.
Oh, no, you're good. No worries.
Sorry.
So I'm just rewriting it. 2 gigahertz. The gigahertz, the giga stands for 10 to the 9. And you can do the same trick as we did before. If you flip it into the numerator, you change the sign to a -9. And this is the same as saying a half times and then 10 to the -9. Remember, that's nanoseconds. So it's half of a nanosecond. Now, you'll notice that I put 500 picoseconds here, and this is half a nanosecond, but those are the same thing. If you were to, again, divide this by 1,000 to go down to picoseconds, multiply this by 1,000 to go down to picoseconds, 1,000 over 2 is going to be 500. And so you get 500 picoseconds. Or in other words, half a nanosecond. 1 nanosecond is 1,000 picoseconds, so half a nanosecond is 500 picoseconds. So that's one way you can get it. And so what we're saying is that 500 picoseconds needs to be greater than or equal to this right-hand side. And the only thing we don't know is t-skew. So we got to do a little algebra here. So we know that this stuff is 430 picoseconds. How would we get what the maximum value of t-skew is?
Move everything. Well, I guess the easier thing would be it's 7.
Not 7.
70. Sorry.
Yeah, 70, yeah. It's going to be 70 picoseconds. We can go less for sure. It can handle less skew than that. But this is the maximum, 70 picoseconds.
Okay.
Yep, and that's about it for that operation. Let me think. There was one other minor point that I wanted to add on, which is the direction of the skew. Do you know which clock received the value first? Like which one came earlier, based off of the information that this is the side where we added the skew to? Because you can figure it out, but I'm just curious if you know how to.
Oh.
Let's talk about it real quick. So I'm going to do, this is what the left register sees, and this is what the right register sees. So you'll notice that in my diagram, I have that the skew is to the right. So if I were to draw it out in a schematic, it would look like this. Do you know what that triangle symbol I just drew there is?
Buffer.
Yeah, it's a buffer. That just means that this clock is delayed by a little bit compared to that one. And so we have some combinational logic running between the two. And all this means is that register 1 receives the clock value earlier than register 2 does. So let's think about the clock time here. TC greater than TPCQ plus TPD plus T setup. What we want to happen, or what we have to happen, is that before this clock edge hits, we need to have all of these delays already done and over with, because these delays are the worst possible case for sending a signal from the first register to the second register. So once the second register's clock edge hits, these delays need to have already passed, because if they've already passed, then that means the value on this wire is sitting there and stable. Sound good?
Mm-hmm.
So let's mark out those delays. Remember, these begin at register 1, so I'm going to draw them starting from register 1. Say this is TPCQ. Call this TPD. Call this T setup. Is this time good or bad? Like, does this work?
It's passing the first clock edge.
It is. But which register are we
So-
reading into?
Oh, the second one. I see.
Yeah. So we actually care about this clock edge in terms of if we're checking if our timing constraints are working. Because we start the delay from this one, because this is where it reads out of, but it doesn't read back into the same register. It reads back into a different one. So that's why I'm looking at this other one. So will this clock cycle work, that timing?
Yeah.
It will, yeah, because we're still before my clock. But what if there was no skew? What if the clocks were exactly aligned? Would we still be good?
No.
No, because it occurs after the clock cycle is finished, and so it's not ready in time. This is an example of beneficial skew. This is the best case scenario for the clock time. So, as like a shorthand way to remind yourself of this, if it's skewed to the right, meaning the register that's reading has a later time than the register that's outputting. So if this one has the clock come later, then you're doing best case skew.
Hold on, my headset disconnected.
No worries.
Sorry.
You're good. Don't worry about it. Just let me know if you can hear me or not.
Hello?
Hello, can you hear me?
Yeah. Okay.
All right, cool. So yeah, I was just saying that this is the best case scenario for the clock time, because as we just saw, adding in that extra skew made it so we could get we could still have the same clock time. Whereas if we had no skew, we would have had to increase the clock time to account for the fact that this is too long.
Okay.
So this is the best case when it's right-handed skew, like in this direction. This is the best case for TC. As a shorthand thing, and I can explain it to you if you want, the reasoning, but whenever you have the best case for one of the constraints, it's always the worst case for the other. So this is the worst case for the hold time constraint. So this makes it worse. Now, remember, for the best case for TC, that would be adding it over here, t-skew. We said before that the worst case for TC was adding it over here, so that means we add it over here for the best case. You could alternatively write that as subtracting it from the right-hand side. So this is the best case scenario, and it's when it's pointed in this direction, when the skew is going to the right. However, it's going to be the worst case for the hold time. Sorry, did you have a question?
No, I said, oh, okay.
All right. So this is going to be the worst for the hold time, and I'll show you why. TCD. And we're going to have to analyze this again and basically ask ourselves, okay, where is it best to have the skew? So where do you think? Is it best case scenario to have the skew on the left or to have it on the right?
To have it on the right. Wait.
It's okay to not know. A guess is fine.
No, it's just a little bit of brain fog. Sorry.
No, you're good. This isn't a particularly easy topic to learn at first, so it's all right. So let's maybe analyze it with skew on the right.
So it's better for the hold time to be shorter. So it's better for T hold to have, or sorry, for the skew to be on the right side.
Yeah, so let's say we had a hold time of 55, and these two were 50. Ordinarily, without skew, it wouldn't work, right? Because this isn't less. But if we added skew of 10 picoseconds, suddenly the hold time constraint is now met, and that's better. So what that means is it's the exact opposite as we had before, and you could probably guess that from the orientation of the inequality. But for the clock time, if you add to the right, that's bad, but if you subtract from the right, that's good. It's the exact opposite over here. If you add to the right, it's good, but if you subtract from the right, it's bad. So if I subtracted the 10 picoseconds and this was like 45, without skew, it would have worked because 45 is less than 50. But now, if you are subtracting 10 picoseconds, now 45 is not less than 40. And so subtracting skew from the right-hand side is bad. Now, if we were to analyze it in our circuit, we would actually find out that this specific orientation results in bad skew, or worst case scenario skew for our hold time. So it looks something like this. Again, I'm going to draw the same diagram out, just a little bit smaller and over here. So the orientation of the skew is exactly the same. The second clock receives it slightly later. And we're going to say, okay, here at this clock edge, the second clock has just received its clock edge. And so now, like we said, there has to be a hold time after the clock edge for 2, where the signal, our input value, whatever it is, has to be steady, right? But that signal begins and comes from register 1, because it's reading out from register 1, going through logic, and then going to the second register, right? So what that means is, in this particular scenario, you'll notice that register 1 actually reads out its value before register 2 reads in the value because of the orientation of the skew. So our next value that we're trying to read out to the second register starts reading here. And let's just say that it has a super, super, super short delay. So say this is the total contamination delay to go from outputting from this register and going through the combinational logic. Well, at this time, it's going to mess up the hold. Yeah, exactly. What if they were aligned, though? If they were aligned, then we'd have it look like this, like that, that, that. And this hold time would actually still be fine. Moving over this clock in the right direction messed with our hold time because now our contamination signal can get there even faster than before. Because it kind of has a head start in the race. This starts skew amount of time before this guy starts. So it's the worst case scenario.
So there's like a golden like number for the TC and T hold, like a right? Like a
Like a golden number of skew, you mean?
yeah, a golden skew,
Yeah,
right?
where it's like I haven't violated my hold time constraint, but I've allowed enough skew to maybe increase my clock time. Typically, though,
Okay.
skew impacts more things than just these two equations. So, generally speaking, in design, you just try to minimize skew as much as possible. You just don't want any skew, so you don't have to mess with it.
Okay. Okay.
But theoretically, yeah. Yeah. Um, Now, just as another side note before I end the office hours, going in the other direction, the clock skew behaves exactly opposite of what we talked about here. So, in the first case, where it's skewed to the right, we would have the best case scenario for TC and the worst case scenario for T hold. When it's biased to the left, when it's skewed to the left, then it's going to be the worst case for TC and the best case for T hold.
Okay.
And if you want like a simple way to remember this without having to derive it on the spot, if it's biased to the right, the skew, then you add a term onto the right for both equations. You do plus skew on the right. If it's biased to the left, you subtract skew from the right of both equations. If that
Okay.
helps you remember, that works for me. You can think of right as going positive, like on a graph, in the positive x direction and in the negative x direction, if that
That
helps.
does help.
So while I am saying that to make it easier for you to remember on a test, it's still important to know why we add or subtract skew from the right hand side. It comes from these diagrams and analyzing them as we just did today.
Okay.
All right. I think that's what I wanted to talk about, and that'll help you with the next set of problems. Because the next set of problems, it's asking for the worst case scenario for the hold time constraint. Because before I was asking for 2 gigahertz. We want to run it at least at 2 gigahertz, and so we consider the worst case for this, which is the best case for the hold time. But now we're asked, consider the worst case for the hold time. And we want to know how much skew that can tolerate. And remember, the worst case is when you subtract from the hold time. So you can plug in the numbers pretty easily. You already know this one, you already know that one. You just need to figure out what this value is, the most you can subtract from this before the left-hand side is not less than the right-hand side anymore. And that's pretty much it.
Okay. All right. Cool. That makes sense. Thank you.
You're very welcome. All right, I'm going to go ahead and end office hours now. You have a good rest of your day.
You too. Thank you.
Yeah,
Bye.
bye.